Good afternoon. My name is Sara Carrigan, and I will give a short presentation on the life cycle analysis of number 4 Findlater Street. I've worked on this analysis alongside and under the guidance of Alberta Congiduti, who is expert in this field and also lectures in it at TU Dublin. It is not a completed assessment, but there are nonetheless interesting insights and learnings to be had, which I will share. I will provide a brief introduction to life cycle analysis, some information on data source, followed by results and findings, a comparative analysis, and wind up with some of the key learnings from this assessment. So what is a life cycle analysis? A life cycle analysis is essentially a methodology used to evaluate the environmental impact of a product or product system, and a building could be described as a product system. In this case, the product system is a cottage, is Joseph's cottage. In the case of construction, the analysis will cover the construction methods, materials used, waste and pollutants produced, and energy use across the building's whole life cycle. As we don't always have all the information necessary, LCA uses scenarios and assumptions when specific data is not known. This assessment has been carried out in accordance with EN 15978, which looks at the building's products and materials in a system. The standard provides a modular approach to the assessment of environmental impacts, within which are 4 key stages, commonly referred to as cradle to grave. These stages broadly cover product manufacturing, construction operations, building use, which includes operational energy, and end of life. So when we talk about impacts from operational energy or operational carbon, we are looking at the B6 and B7 stages, while embodied impacts from energy or carbon relate to all the other life cycle stages collectively. There are a lot of indicators used to assess environmental impacts, and the standard provides for 6 of these. In this presentation, I will focus on global warming potential, also known as the carbon footprint, and it measures carbon emissions. I will also look at biogenic carbon storage, which measures the potential for embodied carbon to be stored in materials. To carry out this assessment, we have drawn data from as-built drawings and specifications, material quantities from the BIM model, energy consumption, and from the PHPP model. Scenarios and assumptions cover transport distances, and these are the distances from the place of manufacture to site, construction site operations, and end of life. The tool used for the analysis is One-Click LCA, which is an EN 15978 certified tool. And just to note again, this is work in progress, and with that, all impacts from material transport and manufacture are localized to Ireland. There are many different ways to examine results, and the first of these are embodied carbon results at a glance. So this first image provides a benchmark comparison for the cottage. Only certain stages are considered, as the variability in others prohibit comparison. So excluded are construction operations, repair and maintenance, and operational energy and water use. So these results provide a comparison to a national average equivalent building, and in this respect, the cottage scores very well. Then we can consider results by life cycle stage, and as expected when operational energy impacts are out of the picture, the product manufacturing stage dominates. As noted, transport distances are set to account for emissions as if all materials originated in Ireland, and this is reflected in the very low impact for this stage at just 1%, which clearly demonstrates the value of local material sourcing. We can also see results by structural element within the cottage. We can see that horizontal structures dominate, and interestingly, vertical structures are relatively low considering the large facade area of the cottage. This is due to the retention of existing walls and foundations. We can then look more closely at the results by examining each of the life cycle stages. This excludes operational energy use. As seen in the previous slide, the product manufacturing stage is dominant, representing 66% approximately of all embodied carbon emissions. We can also see the carbon storage potential of the materials used in the cottage, and they have the potential to offset up to 80% of the product stage emissions. When we do include operational energy into the results, we can see it dominates by a factor of 25 approximately on the product stage. However, the scale of this magnitude is amplified by the low embodied carbon materials Joseph has used, and that no renewable energy sources are included yet. Embodied carbon results by classification. These again exclude operational energy. Materials are broadly classified as foundations, vertical structure, finishes, and so on. When we look at the massive use of these classifications, external walls and facade dominate by a factor of 5 approximately on the next classification. This is as expected, as there is a significant external wall area to the cottage. We can then look at carbon emissions relative to the same classifications and see that external walls and facade have a relatively low impact considering their high mass of use. This is attributable to the retention and reuse of the existing cottage walls, which means there are no emissions from either the product manufacturing stage, as the material has already been manufactured, nor the transport or construction stages, as the material is on site already in its built form. And this clearly demonstrates the value of material reuse. This table shows the top 8 materials out of a total of 25 that contribute most in terms of embodied carbon emissions. The floor adhesive has a high mass of use and high emissions per meter cubed, and this identifies it as a hotspot. If you are at early design stage, you might look to select an alternative product with lower emissions per meter cubed. On the other hand, cellular glass aggregate also has a high mass of use, but has low emissions per meter cubed, and this is the ideal scenario. Hotspotting is really useful at early design stage when you still have the opportunity to select alternative materials. The target would be to have no red clouds. However, even at early design stage, it might not be possible to achieve this, as suitable alternative materials with the technical characteristics required might not yet be available on the market. So in order to understand what results mean and put context on them, comparisons can be really useful. In this respect, we made 2 changes to the model that could be broadly described as mainstream approaches to see how the results would differ. Firstly, we swapped out some of the insulation materials for mainstream equivalents. So cellulose was replaced with mineral wool, wood fiber boards were replaced with PIR, and the recycled cotton was replaced also with mineral wool. And then we added rebuilding of the existing concrete walls and footings. We focused the analysis on the product manufacture stage, as this is the dominant stage in terms of embodied carbon emissions. Total emissions increased by a factor of 3 approximately from the as-built situation. This, put another way, represents a 68% saving in embodied carbon emissions on the approach Joseph took with construction relative to what could be described as a more mainstream approach. In terms of building element, foundations increased by 86%, external walls and facade increased by a factor of 10, or external walls and facade increased by a factor of 10, internal walls increased by 26%, and floor slabs and roof increased by a relatively modest 6%. The greatest emission increase was by far across the external walls and facade, which is primarily due to rebuilding the concrete walls, which are accounted for as existing in the as-built scenario. Notably, carbon storage reduces by 27% due to the replacement of the wood component of the insulation materials. So in summing up, the life cycle analysis tells us a number of things. Local material supply should be targeted, and the results show an optimum situation where all materials are sourced in Ireland, and this was reflected in very low emissions for the transport stage. Carbon storage potential increases when wood-based materials are used, and this was demonstrated in the insulation material swap out, where carbon storage reduced by 27%. Materials should be reused wherever possible, and we saw this in the very low emissions for the facades, which included the existing concrete. Materials with low embodied carbon should be targeted, especially in situations of high mass of use. An LCA at early design stage will help identify hotspots and set overall emission targets for the building. And finally, this presentation focused mainly on embodied carbon emissions, which are measured in terms of GWP. However, as I mentioned earlier, there are 5 other indicators that the standard also considers. And as the table shows, when considering the as-built cottage in blue against the version with the material swap out and rebuild in orange, we can see that the measures we take to reduce carbon emissions will also have a positive impact on all the other environmental indicators too. Thank you.